Hi everyone, today we are talking about volume, and this is an extension of finding area. And so we have some pictures right here, and you can kind of see what's going on. With these, we're going to have some kind of two-dimensional shape here, some kind of area. You can see that right here. It looks like I have a parabola, an upside-down parabola, like 4 minus x squared maybe. Right? And from the area, I can kind of use this as a base and then take some sort of geometric shape that we're already aware of, in this case semicircles, and then kind of sprout semicircles from my area here as a base. Okay, so I'm basically taking cross sections here. So I can see right here I basically have rectangles. I'm calling these cross sections, and I'm using these cross sections as a base for my geometric shape. And then I'm going to take a million billion of these geometric shapes, add them together, and I get a volume of a three-dimensional object. So basically we're going from 2 dimensions to 3 dimensions, okay, using what we know about area. Okay, so for cross sections that are perpendicular to the x-axis, okay, so meaning, well, you'll see what we mean in a minute, our volume is going to be the integral from a to b of my area. Okay, so like I just said, we are going to be taking a bunch of these shapes and then adding them all together, and that's what the integral does. It basically does an infinite summation for us. Okay, and then for cross sections perpendicular to the y-axis, we're going to go from, we'll say y equals c to y equals d. That's very common. Okay, so these are just y values of our area with respect to y. All right, that's the only difference. So perpendicular to the x-axis with respect to x, perpendicular to the y-axis with respect to y. So there's a really good applet right here, and we'll take a look at it. And so what's happening is, for instance, here are my functions. I have 2 functions here. Okay, and so this is what we did in the last section where we just found area. Now we're taking that and we're using this area as a base for basically another area. So right here, I can see that this bottom plane is my base, and I'm using this as a plane to create an equilateral triangle. Okay, and the goal is to find like the area of my equilateral triangle here, and here, and here, and here, and here, and all the way down, wherever my bounds are, add them all together, which is what the integral does, and then it finds me the total area of my solid. All right, that's the goal. All right, so let's actually do some practice. Okay, so first example, I'm given a parabola. So x squared looks something like that, and then negative 2x plus 3. So a linear function going down looks something like that. All right, so here is my area. And what I'm doing is I'm taking cross sections perpendicular to the x-axis for first rectangles of a height 4. Okay, so again, what I'm doing is I'm taking cross sections that look like this, perpendicular to the x-axis. Okay, so if you can imagine, this is us looking kind of at a bird's eye view. I'm looking from above. This is my cross section. Okay, and if I look at it straight on, really what I'm seeing is a bunch of rectangles with a height of 4. Okay, so kind of think about it as this is my width right here. This is my width, this distance, and then my height is 4. Okay, so it's kind of, if you can imagine the perspective here. Okay, so really I need to know what this distance is because that's going to be the width of my rectangle, and I need to know the area of this rectangle. And so that goes back to our idea of area, so top minus bottom. So in this case, it'll be negative 2x plus 3 minus x squared, okay, top minus bottom. All right, and so this is my rectangle. These are the dimensions of my rectangle, 4 by negative 2x plus 3 minus x squared. Okay, now to actually find the volume, I need to do a couple things. First, I need to find my intersection points. So I'm going to set negative 2x plus 3 equal to x squared and solve that out. Oops. Right, so we can factor this, and I get negative 3, and 1. So those are going to be the bounds of my integral. Right, and then on the inside, I just put my area. Okay, and it's going to be the area of my rectangle. Now we just said that the dimensions of my rectangle are as listed, so the area is just my height times my width, which is negative 2x plus 3 minus x squared with respect to x. Okay, so what I'm doing is I'm putting in my two dimensions right here, my area. Okay, this is two dimensions. The integral is going to evaluate the area at every single point along here between these bounds. And it's going to turn my two dimensions into three dimensions. All right, we can do the same thing for a semicircle. So again, this picture doesn't change here. This is still from above. This is still my cross section. But if I view it straight on, instead of rectangles, this time I have a semicircle, where this bottom diameter is negative 2x plus 3 minus x squared. Oops. Okay, minus x squared. Well, I know the area of a semicircle is going to be 1/2 pi r squared. Okay, so my area in terms of x is going to be 1/2 pi. Now my radius is going to be my diameter divided by 2. And I know all this is my diameter. So negative 2x plus 3 minus x squared divided by 2. And I'm going to square this. So there's my 1/2 pi r squared. So this is the area of any given semicircle in this region. And again, I just have to set up an integral. So integral negative 3 to 1, 1/2 pi, negative 2x plus 3 minus x squared over 2 squared with respect to x. Right, and again, this is my area, two dimensions, and the integral turns it into, basically gives us three dimensions. Okay, it does the area like a million billion times between negative 3 and 1. Adds them all together. Okay, let's keep going. Next, we're just asked to set up the integral needed to find the volume of a solid bound by this circle whose cross sections perpendicular to the x-axis, so similar to what we've been doing, are equilateral triangles, and they give us the area of an equilateral triangle just given a side. This is very common. So let's draw a picture. Okay, so I have a circle. Okay, this is the worst circle of all time. Let me try that again. Okay, so I have a circle from negative 3 to 3, and I know that the top part of my circle is the square root of 9 minus x squared. The bottom of my circle is negative 9 minus x squared. Okay, and what I'm doing is taking these cross sections right here, and I'm popping an equilateral triangle out of it. Okay, if you can imagine that. Okay, well, if I look at my equilateral triangle straight up, I see that the bottom, so my base here, is this whole distance. Okay, so it's whatever this distance is from the x-axis to the top, which is square root of 9 minus x squared, and then the distance from the x-axis to the bottom, which is right here. So really, it's double the square root of 9 minus x squared. Okay, because this is 1, this is another, so it's just 2 times that. Okay, that is the length of my base. Okay, now I can just set up my area. So the area is going to be the square root of 3 over 4, so that's just this right here, and then side squared, and this is my side. All right, and we could simplify that a little bit, and if you simplify it quite a bit, a couple steps, you'll get to right here. So all I did was square things, and then 2 squared and 4 end up canceling out. All right, so I just need to plug this into my volume. Okay, so I'm going from negative 3 to 3, because those are my x bounds, and then I'm just plugging in my area equation with respect to x. All right, one more. Let's do a square this time. Okay, so I'm bound by y equals x squared, y equals 0, and x equals 2. So y equals x squared, and then I'll say this is 2, this is 0, and this time I'm taking cross sections perpendicular to the y-axis, so I'm going this way. Right, and so each of these is a square, if you can imagine that. Okay, popping up and whatever, it's a square. Okay, so I just need to set up my integral. So because I'm taking cross sections perpendicular to the y-axis, I need my equation in terms of y. So I'm going to solve for y. And because I'm only looking at the first quadrant, so everything's positive, I'm just going to look at the positive square root of y. Okay, well, if I think about what my square looks like in terms of its dimensions, remember, when you're doing area, we're still doing right minus left. Okay, so my right is 2, my left is the square root of y. All right, so that's going to be the width right here, 2 minus the square root of y. That will tell me my width. And because it's a square, the base is equal to the width, or the height, or whatever you want to call it. So this is also 2 minus the square root of y. Okay, so my area, in terms of y, is 2 minus the square root of y squared, because it's just side squared. So for my volume, I am just going to plug that in, and I just plug in my area. Now the important part is my bounds. My bounds have to be in terms of y. So I'm not going to put 0 to 2. Instead, I'm going to put the y bounds. Oops. I'm going to put 0 to 4. All right, so because everything is in terms of y, I have to put my bounds in terms of y as well. All right, that's it for this. See y'all later.